Every echo obeys one simple law. And by the end of this experiment, you'll see it with your own eyes.
Just like a beam of light hitting a mirror, sound waves travel through the air and bounce back when they strike a solid surface. To see exactly how these invisible waves behave, we are going to build a physical apparatus that lets us track and measure their geometric path. Looking at this setup, we have four required components: two hollow tubes, a flat reflecting board, a large semicircular protractor, and an analog alarm clock. Before assembling these parts, you must set up in a completely silent room. Any background noise will corrupt the delicate auditory data we need to collect. By constraining an invisible sound wave within these tubes, we can measure its exact path along the protractor. This data will definitely prove the laws of reflection of sound. Let's begin the first trial. Take the first tube, which will guide our incoming or incident wave, and align its lower opening to exactly the 20-degree mark on the protractor. Looking at this vector schematic, notice how the 20-degree angle is measured strictly from the 0-degree center line to the inner edge of the tube. Reading the measurement from the outside edge will distort our results. Next, place the ticking alarm clock exactly at the outer mouth of that first tube. Make sure the face of the clock sits perfectly flush against the opening. Creating this flush seal is vital. It prevents acoustic leakage into the room, forcing the entirety of the sound wave's energy straight down the cylinder toward the reflecting board. Now, place your ear at the opening of the second tube. Slowly sweep this tube in an arc across the opposite side of the protractor. As you move the tube, listen closely for a very specific sweet spot. You are sweeping for the exact angle where the ticking achieves maximum volume and absolute clarity. Once you isolate that clarity, check the protractor. The tube locks in at exactly 20 degree. We now have our first baseline measurement linking the input path to the output path. A single matching data point does not prove a universal scientific law. To establish a reliable pattern, we have to run a stress test at a wider angle. Reset the physical apparatus and move the first tube outward until its inner edge rests exactly at the 40-degree mark. Double check your sound source. The alarm clock must remain completely flush against the tube at this new steeper angle. Place your ear against the second tube again and repeat the slow sweeping motion across the opposite side of the measurement track. When you pinpoint the peak audio clarity, this time the second tube will align perfectly at the 40-degree mark. During this wider sweep, some users struggle to find the exact peak volume. Ambient room frequencies can often interfere with the sound traveling up the tube. That is why we use a mechanical alarm clock. A sharp rhythmic ticking cuts through those ambient room frequencies much better than a continuous tone. Our 20-degree input yielded a 20-degree output and a 40-degree input yielded a 40-degree output. The acoustic reflection predictably follows a rigid mathematical symmetry. This diagram illustrates the second law of reflection of sound, which states that the angle of incidence is always equal to the angle of reflection. You can see the sound travel down the first tube, bounce off the flat surface, and travel up the second tube, maintaining equal angles on both sides. The physical measurements we just took mapped directly to this law. At our baseline, the angles lock in at 20 degree equal to 20 degree. When we widen the stance, it precisely scaled to 40 degree equal to 40 degree. The first law of reflection mandates that all elements of this bounce must exist on the exact same plane. Notice how the entire track rests completely flat on the table beneath the tubes. There is one final theoretical component to this first law. The dashed line you see animating downward is called normal. It is an invisible perpendicular line drawn exactly at the point where the sound hits the wall, bisecting the two tubes. Look at your physical setup from a low side profile. Verify that both tubes and the protractor lay completely flush against the table, because the incident wave, the reflected wave, and the theoretical normal line all clearly share this single flat surface. You have physically satisfied and proven the first law of reflection. You have successfully constructed a functional acoustic reflection chamber. By meticulously placing the components and recording the angles, you validated theoretical physics with hard physical data. This simple desktop setup tracked an invisible wave of air pressure, proving it bounces off a solid barrier at the exact same angle it arrives. You can now modify the experiment's variables. Try replacing the hard reflecting board with a textured acoustic foam panel positioned vertically at the ends of the tubes. This allows you to measure acoustic decay instead of a clean bounce. Measuring these two simple laws of reflection provides the foundation for engineering the acoustic of our world. It is the starting point for everything from designing pristine concert halls to developing advanced noise cancelling technology.